for a little while. All right, so we were doing page 321, number 12. Okay, and we had this wonderful loop-de-loop thing where we released our marble up here from some height h, and the marble came around to, I think this is point T, around a loop of radius capital R. And this is the point where the marble is just about to leave the track. So we said that that meant that the magnitude of the normal force went to 0. And because this is a physics class, we drew a free body diagram. So we had Fg, we had that normal force that we let be equal to 0. And I think we figured out that V center of mass squared was equal to GR. Does that look familiar? And I believe we had G was equal to V center of mass squared over R. That look right? Okay. And then after we used Newton's law, we moved on to kinetic energy, I believe. No, I'm sorry, regular energy and conservation of energy. So we compared what was going on up here at point 0, which was the release point, and point T, right? And this was the part where you all failed me miserably, I believe. And we talked about how the energy at point T, total energy at point T had to be equal to the total energy at point T. And so we said that we had a whole bunch of kinetic energy up there at H. And then we had some potential energy at point T. And then what was the problem that I messed up and nobody found? Yeah, that we had two kinds of kinetic energy. We had rotational kinetic energy and we had translational kinetic energy. And I believe that that is where we were, ish. Okay? So we had mgh for our initial potential energy. I think we had mg2r for our potential energy at T. I remember asking somebody to justify that, right? Because if the radius of the loop is r, then this distance is going to be 2r. Yes? We were there? Okay. And then, what's my formula for rotational kinetic energy? Okay, so 1/2 I omega squared. And what's my formula for translational kinetic energy? 1/2 m, and this is going to be V center of mass squared. Okay? I think this was where we got into trouble, because we hadn't done this. So I've got mgh is 2 mgr. But I have a little bit of a problem here, right? Because h is what I'm looking for, but I don't know what omega is. What am I going to do about omega? V center of mass. Okay, the radius of what in this situation? Because what's the ball doing? It's the radius of the marble, or the ball, or whatever it is. Not at this moment and not at this time. Okay. And then I've also got this problem with I. If I could write I somehow, then I could cross off all my M's, right? So what's a marble? What kind of shape is a marble? A sphere. What kind of a sphere? If you think a solid sphere, as opposed to a spherical shell. So what's I going to be for that for that solid sphere? Yep. I think we did that part too. Okay. And it's the little r because it's the radius of the sphere. So if I substitute all that in, I've got 1/2 times 2/5 mr squared. And omega squared is going to be v center of mass squared over r squared. What's up? What I want to do first is I want to cancel those r squareds, just so that they're out of the way. Okay. And then, yeah, I've got a mass in every term now. So I have GH is 2GR plus 1/5 V center of mass squared plus 1/2 V center of mass squared. This? That's the potential, the gravitational potential energy here. Because I let UG grav be equal to 0 at the bottom of the loop. All right, so am I done? No, what am I going to do? Do I have a value for V center of mass? Or V center of mass squared? What did I write down at the beginning? What did we figure out when we applied Newton's second law? What did I write, though? That's not what I wrote, though. What did I write? The V center of mass squared was equal to GR. So that means I can come over here. I've got GH is 2GR plus 1/5 GR plus 1/2 GR. And I can cancel all my G's. So that H is going to be 2.7 times R. And that's some number, and I don't care what that number is. Okay. 2 plus 1/5 plus 1/2. All right. We good? We got it? All right. So there's a part B to this. What does part B ask us? If I release it somewhere, right? So I'm going to release it. It's going to go like that. I think the point that I released it from up here, don't they tell you that H is equal to 6R? I think they tell you that. Yeah? Okay. Okay, and then my object is over here at point Q. And what do we want to know? Of the... Okay, so if there's going to be a horizontal force this way, what is that force? Yeah, but what's causing it? Nope. Look where it's pointing. It's perpendicular to the normal force. It's perpendicular to the interface. Okay. Now, there's also, of course, a gravitational force pointing down, but that's not really going to help me with what I'm trying to do right now. Okay. So Go was right in that this object is undergoing centripetal motion. Okay, and that centripetal acceleration is going to point towards the center. And so it's going to be the normal force that is responsible for that. We can say that F net is going to be MAC. That's going to be the normal force. So the normal force is going to be MAC. And what's the formula for AC? V squared over R. Okay, and again, it's going to be capital R, the radius of the loop. And again, we're still going to have that little r, the radius of the marble, is much, much smaller than big R. So I don't have to worry about how the center of mass really makes a slightly smaller circle. Now we're going to assume that I know M and that I know R, but how am I going to find a value for V center of mass? No, because this is a different situation now. So I can't, and I've already done that. I've already applied Newton's second law, which was how I got V center of mass the first time. Well, I'm trying to find N, and I'm going to assume that I know the mass of the marble and the radius of the loop. So if I'm going to figure out the magnitude of N, I need to know what the center of mass velocity is. Yeah, we could do conservation of energy again. Okay, and say that the energy at 0 is going to be equal to the energy at Q. Okay, so we're going to have potential energy up at the original point. We're going to assume it's released from rest, so there's no kinetic energy. I'm going to have some potential energy at Q, and then we're not going to make the same mistake again. At Q, we're going to have some rotational energy, and we're also going to have some translational energy. Translational kinetic energy, excuse me. So what's my potential energy up at point 0 or at point O? What's my potential energy at point Q? Again, assuming that UG is equal to 0 at the bottom of the loop. MGR. What's my formula for rotational kinetic energy? And what's my formula for translational kinetic energy? Yep, V center of mass squared. So the algebra is pretty much the same as it was last time. Although I'm going to take this and move it to the other side. So that's going to give me 5 mgr, right? Because I'm subtracting it from an mgr from both sides. Well, I'm going to put in the rotational inertia of a solid sphere again, which is 2/5 mr squared. And then, yes, you're exactly right. We're going to take omega, and we're going to make omega squared and make it V center of mass squared over r squared plus 1/2 m V center of mass squared. And then there's a whole bunch of algebra we can do and a whole bunch of things we can cancel. So I can cancel my little r squareds. I can cancel my 2's. I have an m in every term now. So I've got 5gr is 7/10 V center of mass squared. I think that's right. 1/5 plus 1/2. Or V center of mass squared is 50/7gr. Okay. We good? And remember, we said a couple minutes ago that my normal force was mv center of mass squared over r. Let's just write that again on a new sheet. What was it? I've lost it already. mv center of mass squared over r. And our V center of mass squared was 50/7gr. My r's cancel, so I get that the magnitude of the normal force is 50/7 mg. Okay, we good? We got it? It kind of makes sense in that what are the units of normal force supposed to be? Newtons. And what will the units of mg be? Newtons. Okay, so at least we know that we've got our units going in the right direction. Okay, so I think I'm going to do one more thing. It's kind of a start for what we'll do tomorrow. I'm going to teach all day tomorrow, and that'll actually be a good thing because we can do something in a whole chunk. But we want to go back and talk about torque. And finally turn torque into an actual vector and deal with the torque on objects that aren't just moving in a circle. So I'm going to give myself a coordinate system here. X, Y, Z. Please note that X is coming out of the board. And that's actually really important. And this is a situation where you do not get to choose what this looks like. Okay. So I've got a particle here at point A, and it's located at some position vector r from the origin. And it's moving around the origin. Doesn't matter. And it's going to be acted on by a force F. That makes an angle phi with the direction of r. Now this should look familiar. R is going to be your moment arm. F is going to be that applied force. And you know that that's going to give rise to a torque. But we're going to have a new way of writing this. And we're going to say that that torque is going to be equal to R cross F. You can still write the magnitude as RF sine phi if it makes you happy, and sometimes it will be useful. But in using this cross product, it will enable us to find the direction of the torque. This is actually kind of fun. I know it doesn't seem that way right now, but it's actually pretty fun. And that fun shall have to wait until tomorrow.